Okay, I think we are going to go ahead and get started. Anyone else who is coming in late, they will just have access to our recording, but they can join in at any time as well. All right, welcome everyone. Thank you for joining us. My name is Michael. I'll be your host for today. I am a cloud solutions architect from MassDriver. MassDriver is a visual internal developer platform that enables engineers and developers to deploy production-ready cloud infrastructure and applications in minutes. During the webinar, our CEO, Corey O'Daniel, and our COO, Chris Hill, both co-founders of MassDriver, will be in the chat and QA rooms answering any and all questions. All right, today we'll be talking about how to get started with Docker and the best practices for containerizing web apps using Docker. Specifically, we'll cover some basics of Docker and the Dockerfile. We'll go over some essential Dockerfile instructions, and then we'll finish the presentation on Dockerfile best practices. We'll end the webinar with a live demo on deploying a Dockerized application onto an Azure Kubernetes cluster using MassDriver. Without further ado, let's get started. So, what is Docker? In short, Docker is a tool that allows users to easily deploy their applications in a sandbox environment, aka a container, to run on the host operating system. The main benefit of Docker is that it makes it easy for users to repeatedly and consistently package an application in a controlled, virtualized environment that can be ported to a vast variety of runtimes. Now that we have an idea of what Docker is, let's talk about a Dockerfile. So the Dockerfile is a text document that contains all the commands a user could call on the command line to build a container image. It's basically a script of step-by-step instructions. Let's look at this example here. Starting from the top, we have a line that is commented out. This comment is a Dockerfile parser directive. It specifies which version of the Dockerfile syntax to use. This file sets a Dockerfile version of 1, which keeps updated with the latest minor and patch releases to ensure that you have access to the latest Docker build features. Docker will treat any line with a # as a comment unless it is a valid parser directive. A parser directive is optional, but it does affect the way in which subsequent lines of the Dockerfile are handled. Lines 2 through 8 are the instructions of the Dockerfile. Each line is a separate instruction to run, and each instruction defines an image layer. Looking at the sample, we have an instruction labeled from and an argument that defines the Golang base image with the specific version. The instruction tells the container which action to take, and then the argument populates the action with the data necessary to complete the step. The instruction is not case sensitive. However, it is best practice to make all instructions uppercase so that they are distinguishable from the arguments. Docker will run the instructions within the Dockerfile in order, and a Dockerfile must start with a from instruction. Now let's briefly talk about layers for a minute. This image shows how a Dockerfile translates into a stack of layers in a container image. The ordering of instructions matter as they determine how to build the image, and each instruction within the Dockerfile is essentially a layer. We'll discuss how to take advantage of this system in a little bit. Let's cover the Docker CLI here next. The Docker CLI is a tool used to interact with the Docker daemon. The Docker daemon is the process that manages containers and handles all of the commands sent from the CLI. Let's run through some of these commands in a terminal. I'm just going to share my screen for my terminal here. And then here's my terminal. We have, I'm in my Docker folder. If I do ls, there's nothing in here. So first let's run Docker version. Docker version will populate what version we're running. Great, we're up to date. Now let's pull the official Mongo image from Docker Hub. I'm gonna do Docker pull Mongo. And this will just take a few seconds here. I've already pulled a lot of the layers already, so that was pretty quick. And now that I have my image locally, I'll go ahead and run the image in the container and map port 80 to 8080. To do that, I'm going to type docker run -d. -d allows the container to run in the background. And then we'll do -p for port 8080:80, and then interactive with Mongo. Okay, so now it's given us a hash result. We can do Docker PS to find out what containers we have up and running. And there we go. We have Mongo container up and running with port 8080 mapped to port 80. We can exec into this container, kind of like we do with a virtual machine, using the exec command and the container ID. So to do that, I'm going to type docker exec, and then I'm going to do -it. I'm going to grab the container ID here, paste, and then I'm going to specify that I want a bash connection. And there we go. So I'm execed into the container. Now what I can do is I can type mongo d -- version, and we can see that I am running Mongo version 6. I'll go ahead and exit now. I can stop the container using the same container ID and the stop command. So if I do docker stop, and then we'll paste in the container ID. Okay, we get a confirmation. If I do docker ps again, which lists all of my running containers, we can see that I don't have any containers up and running. Okay, now let's go ahead and create a Docker file here. I'm just going to nano a Docker file. We have a blank Docker file. I'm going to copy in this basic Docker file here. So what this Docker file is doing is it's setting the syntax of 1. I am pulling the Golang base image, and then the other commands, I'm basically running an application, and we'll go through the essential Docker file instructions a little bit later. I'm going to save this here. And then I also need to create an app. So I'm going to do hello world.go. I'm going to paste in my go function. And then we're going to save this as well. So, okay, so we have my Docker file, we have hello world app. Let's go ahead and test this. We'll do go run hello world.go. Perfect. So we're going to build this out, hello world.go. And then if I run the app, hello world, perfect. So what we can do next is we can build the Docker image. So I'm going to do docker build -t sets the tag. This lets me to label my image. mc_lacor, that is my personal Docker Hub account. And then hello, that's going to be my Docker Hub repository. And then I'm going to add a dot at the end, which technically sets the build context. I'm basically telling the Docker build command where my Docker file is located. I'm going to go ahead and run that. It's going to build out the image. Perfect. Now I want to push my image up into my Docker Hub repo. So if I do docker push, and then I'm just going to set my tag that I set in my build, which is my Docker Hub account / the repo, and hit enter. And it's going to push it up to my Docker Hub account. It's taking a minute here. Okay, I'm going to go ahead and try to cancel out of this, and then we'll try to run this again. This is an interesting outcome. Okay, I do know that this already exists as in my Docker Hub repository. I'm not sure what's going on with my Docker daemon right now. But it doesn't want to connect for some reason, and that's okay. We'll go ahead and move on here. So to summarize, what we did is we made an app, we tested it, we built the image, And then we pushed it up into, or at least we tried to push it up into my Docker Hub repository. But I do have the image built. So if we do run the image, we should get the same result. So I'll do docker run -it and then set my Docker Hub repo. And then we have the resulting Docker world. Perfect. Let's move on. And then we're going to go ahead and dive a bit deeper into the Dockerfile instructions just to understand what each line means. I'm going to go ahead and swap screens back here. Okay, sharing my screen again. And then, okay, so let's talk about the essential Dockerfile instructions. Choosing the base image. The from instruction initializes a new build stage and sets the base image. Any valid image can be used, many of which can be found on Docker Hub. So looking at the example here, I'm telling my Dockerfile to pull the official Golang image and use the 1.20-alpine tag to set the specific version. The tag value is optional, but omitting it will automatically pull the latest image, and it may not be the version that you're looking for. Executing commands during an image build. The run instruction will execute any command in a new layer on top of the current image and commit the results. The resulting image is used for the next step in the Dockerfile. The line here that will execute pip install AWS CLI is committed into a new layer, and then the results will be inserted before the CMD line, as you can see with the example below. Managing file and directory copying. The copy instruction copies new files and directories from the source path to the destination path. Add will do the same thing as copy, with the addition of copying remote file URLs and extracting a .tar file from the source directory into the destination directory. Let's look at this example here. Line 1 will copy all files in the directory of the Dockerfile into the root directory of the container. Line 3 will create an app directory in the container and then copy the test.txt in the local source directory to the app directory. I know that's kind of confusing, bear with me. Line 5 will create an app directory in the container and then copy the hello world Git repo to that app directory. Also, I've added a flag there. The keep git directory equals true argument adds the .git directory into my container as well. Setting environment variables. The env instruction sets an environment variable in a key value pair format. In this example, I'm setting an environment variable of my dog equals to Roger, which is my dog's real name. And the environment variable set using env will persist when the container is run from the resulting image. If you don't want the environment variable to persist, use the arg instruction instead. You can override the environment variables set in your Dockerfile at runtime by using the docker run -e command and then the key value. In the example here, I'm overriding my dog's name from Roger to Spot. Defining the working directory. The workdir, or the working directory instruction, sets the working directory for all run, CMD, entry point, copy, and add instructions that follow it in the Dockerfile. If the working directory instruction doesn't exist, it will be created automatically and set to root by default, unless it is otherwise specified in the base image. To avoid unintended issues with unknown directories, it is best practice to set your working directory explicitly in your Dockerfile. Specifying expose ports. The expose instruction tells Docker that the container will be listening on the specified network ports at runtime. Both TCP and UDP are supported. However, TCP will be used by default if it is not specified. The expose instruction doesn't actually publish the port. Instead, it functions as a type of documentation to run the container. To publish the port when running the container, the -p flag on Docker run is used. Running commands or scripts at container startup. So finally, we have CMD and entry point. Both CMD and entry point have two forms, the shell form and the exec form, with the exec form being the preferred method. The exec form is parsed as a JSON array, which means that you must use the double quotes around words, and then those quotes need to be within the brackets. Unlike the shell form, the exec form does not invoke a command shell. This means that normal shell processing does not happen. The exec form makes it possible to avoid shell string manipulation. So looking at line 1 here of our example, we have echo $home. Echo $home will not do variable substitution for $home. If you want shell processing, then you need to switch to shell form or execute a shell directly as shown on line 3. When using the exec form, executing a shell directly or using the shell form, it is the shell that is doing the environment variable expansion, not Docker. All right, let's compare these two instructions here. The CMD instruction provides defaults for executing a container. CMD can set params and an executable. If you omit the executable, it must be set in entry point instead. CMD is not to be confused with the run instruction. Run will run a command and then commit the results to the image. CMD does not execute at build time, but rather specifies the intended command for the image. CMD can also be overridden by giving Docker the proper arguments. Entry point is similar enough to CMD, but it cannot be overridden by arguments, and it requires an executable. Entry point specifies a command that will always be executed when the container starts. Let's check out an example of a Docker file here that when run will ping localhost. I'm going to go ahead and switch screens back to my terminal here. Clear. We're going to switch into a different directory. Perfect. So we do ls, there's nothing here. I'm going to go ahead and create a simple Docker file that allows us to run the ping command when using entry point as the command structure and then CMD as the argument. So I'm going to do nano Dockerfile. I'm going to copy in this basic Docker file here. This is just a base Debian image. Like I said, the command is running ping, and then CMD is setting the argument as localhost. I'm going to save it, and then let's go ahead and build the image, docker build-t. We're setting ping as the label there for the tag, and then dot is going to be where my Docker file is located. And it's just going to run for a minute here. Seem to be having an issue with my Docker daemon. That's okay. I do know that I have this image locally if I do docker run -it ping. And it's not found locally. Okay, let's try to do docker build-t ping one more time. Okay, there it's finished. So we docker run -it ping, and then we're going to see it's pinging my local host. Perfect. Now, so it's pinging localhost as expected. If we add an argument, it'll ping the argument instead. So we docker run -it ping massdriver.cloud. We can actually see that it's pinging massdriver.cloud instead of localhost. I'm going to go ahead and update my Docker file, and we're going to change the structure here to just use CMD. So if I copy and paste this, so it's the same base image that we're using, but instead of setting the executable in entry point, we're setting the executable and the argument within CMD. Now let's save this and then we're going to rebuild it. Docker build -t ping dot. And hopefully this builds pretty quickly. Okay. My Docker daemon does not seem to want to participate today. Okay, so we were able to build the update, and then now we're going to run -it ping, and then pinging localhost as we expect. Perfect. Now let's try Docker run -it ping massdriver.cloud like we did before. And what this is going to do is this is going to result in an error saying that it's unable to exec massdriver.cloud. It's looking for a massdriver.cloud executable, which doesn't exist. So let's try running the same command, but with a different argument. So we'll do Docker run -it ping, and then let's just do echo hello world. There it is. So as we saw, the way that we structure the running commands at startup can alter the way we can interact with those commands. All right, let's switch back to my terminal here, or sorry, my presentation here. Okay, and then we're going to go ahead and move on to Dockerfile best practices. So we're going to cover layer caching, the Docker ignore file, and multi-stage builds here. Let's begin with layer caching and optimizing build times. Earlier, we discussed that layers make up a Docker file. Each instruction is essentially a layer. When we build an image, the builder tries to reuse layers from earlier builds. We call this cached layers. If the layer of an image is unchanged, it'll use the same layer from the build cache. This will speed up build times tremendously. If the layer has changed, that layer and every layer below becomes invalidated and must be rebuilt. This is important because you'll likely find yourself rebuilding the same Docker image over and over again, possibly due to preparing the next release of your app or testing an image locally. Building images is a constant task, and caching layers speeds up that process. To optimize your Docker file for efficient builds, we have a few approaches here. We recommend ordering your layers, keeping your layers small, and then minimizing the number of layers. Setting your instructions in a logical order is a solid first step because changing the order at any point requires a rebuild for all steps that follow a change. Steps that change often should be placed near the end of your Docker file. Let's look at a couple of examples here. The top Docker file there on the left is inefficient because updating any file requires a reinstall of all dependencies every time you build your Docker image, even if the dependencies didn't change. In the bottom Docker file, we split the copy command to first copy the package.json and yarn.lock files. We then install the dependencies prior to copying over the project files. By installing the dependencies in an earlier layer, there is no need to rebuild those layers when project files change. Another way to speed up image building is to keep your layers on the small side. You can exclude unnecessary files in your image, only install packages you need, and use the run cache to achieve this. Let's look at the example of excluding unnecessary files. The top example on the right-hand side on line 1, you'll see that line 1 copies your entire build context into the image file system. This will include logs, temp files, etc. Line 3 only copies your source and asset directories, plus the make file, excluding all other files that are unnecessary for your image. The run command also supports a specialized cache, which can be used for a more fine-grained cache between runs. For example, when installing packages, you don't always need to fetch your packages from the internet each time you build. You only need the ones that have updates. Take a look at the bottom example here. We have run mount type equals cache command. This keeps the contents of the target directory preserved between builds. If the layer needs to be rebuilt, it'll use the package tool cache located in var cache apt instead. Another way that we can exclude unnecessary files at image build is to use the .dockerignore file. Before the Docker CLI sends the build context to the Docker daemon, it looks for the .dockerignore file in the same directory as your Docker file. If it exists, the CLI modifies the build to exclude the files and directories that match the patterns within the file. This helps avoid sending large or sensitive files and directories to the daemon and adding them to images using the copy or add instructions. Let's briefly break down this example for the dockerignore file we have here. So comments, anything that's commented out is ignored. Asterisks will include all files and directories in that directory. Question marks act as wildcard characters, and exclamation points will make exceptions. Finally, let's go over leveraging multi-stage builds and how they can be effective. In a Docker file, a build stage is represented by a from instruction. There are two main reasons why you'd want to use multi-stage builds. One, they allow you to run build steps in parallel, making your build pipeline faster and more efficient. Two, they allow you to create a final image with a smaller footprint containing only what you need to run your container. Let's walk through creating a smaller footprint. We'll take the Docker file that we used earlier and we'll modify it a little bit. So in this example here, the change that we made creates a second stage using a minimal scratch image as the base image. In the final scratch image, the binaries built in the previous stage are copied over to the file system of the new image. When you build this image, the size will be significantly smaller than it would be using a single stage. Now that the footprint of the image is smaller, parallelism can help improve build speeds. The file we modified in the last slide produces the binaries one at a time. There is no reason why you need to build the client before the server or vice versa. You can split the binary building steps into separate stages, as we can see in this example here. In the final scratch stage, we copy the binaries from each corresponding build stage. By segmenting these builds into separate stages, Docker can run them in parallel. You can reuse the same image in multiple stages by using the from image as base stage name, and then subsequently using from base stage name as the new stage name. I understand that's kind of hard to follow, but just bear with me. Instead of first building the binaries one at a time, using this method, the build client and the build server will execute simultaneously. The final stage here we have is quite small, and we've used it building with parallelism, but the image is still not quite right, as it contains both the client and the server binary in the same image. We can separate these out into separate images, as we can see on the example on the left. Now we can build the client and the server as separate Docker images using the tag and target arguments we see on the right. Okay, that concludes our presentation on getting started with Docker and the best practices for containerizing a web app using Docker. Now we'll move on to the demo portion of our webinar, where I'll deploy a Dockerized application to Massdriver hosted on an Azure Kubernetes cluster. Let's go ahead and get started here. I'm going to share my VS Code. And what you can see here, this is a basic rock, paper, scissors game that I've written in Python. I have a basic, excuse me. I have a basic Docker file right here that will pull the Python 3.10 base image. It'll install some dependencies for me, expose a port of 5000, and then run the app. I'll go ahead and build my image. I'm going to run docker build -t mcliqueur for my Docker Hub account, and then rps/rps for the repo that I want to build my image for, and then use a dot for the build context, which is telling my command where the Docker file is located. So we're going to build that. Hopefully Docker daemon is responding. It still doesn't want to respond. Let's try that one more time. Perfect. So we built our image. Now I'm going to push it up to my repo /rps. And it's going to hopefully prepare the image and push it up to Docker Hub. This one still may not want to cooperate with me. And that's okay. I do know that I have this exact same image already pushed up in my Docker Hub account. So if my Docker daemon doesn't want to cooperate today, we'll definitely host a webinar at some point, I'm sure, for troubleshooting Docker, because if you're going to use Docker, you're definitely going to need to know how to troubleshoot. But what I want to do now, I know that I have this image in my Docker Hub repo. I'm going to make a new mass driver app using the command mass bundle new. So mass bundle new is going to download a bunch of templates for me, and I'm just going to wait for these to finish downloading. Maybe it's not my Docker daemon, that's the issue. Maybe it's something with my terminal. Let's see, what could be going on here? I'm going to go ahead, I'm going to stop sharing my screen for just a moment, and I'm going to restart my VS Code and terminal to see if I can get it up and running. Just bear with me one moment. Okay, I'm going to reshare my VS Code screen here. And let's try mass bundle new. Okay, here we go. So mass bundle new, it's going to ask me to name my bundle. So I'm going to do rock, paper, scissors, webinar. Why not? This is my rock, paper, scissors game for my webinar. Template, I'm going to select the runtime that I'd like to run this in. We're going to select Kubernetes deployment. And then any dependencies that I need, there's a long list of dependencies that if my application required Mongo database, OpenSearch, Postgres, at my mass driver, we support a plethora of dependencies their application might need. I happen to not need any for my rock, paper, scissors game, so I'm going to select none. And then I'm going to output it into the directory of mass driver. Since I restarted my terminal, I'm going to go ahead and try Docker push again, /rps. Hopefully that goes through. Might just take a minute here. Okay, still doesn't want to cooperate. That's fine. We're going to cd into my mass driver folder here. And if I expand it in my VS Code, we actually populate this folder with template files for my application. So what I want to do now that I have my application created, I want to publish it to my account. So I'm going to use mass bundle publish. We need org ID. Okay, mass bundle publish. Perfect. So now all of the files that my application needs to be able to test locally are hydrated, but now I know that this is actually published to my mass driver account. So let's go ahead and switch over to mass driver. Okay, so this is the mass driver canvas. As you can see, we already have a Kubernetes cluster deployed and connected to a virtual network. I'm going to refresh here just so that my application will get added to the bundle bar. And then let's search for my application. Perfect. So rock, paper, scissors. I'm just going to call this RPS. We'll call this rock, paper, scissors. And then we'll abbreviate it to RPS. This is my funding for my webinar. And hit submit. So we have this neat feature here at MassDriver called the infrastructure generator. Basically, it'll look for all of the bundle dependencies of whatever I'm adding to the canvas and automatically generate and connect the required infrastructure needed to run the bundle you want. My rock, paper, scissors game didn't have any additional dependencies besides Kubernetes. So all it did was automatically connect it for me. But if I had a Postgres or a Mongo database requirement, it would select that specific bundle and then add it to the canvas for me so I can get ready to deploy it. So now that they're connected, I'll go ahead and configure my application. So I'm going to click the configure button. And all I really need to do to get my application up and running is set my repository. So I'm going to do mclicore for my Docker Hub account /RPS for the repo. I'm going to use the latest tag. And then let's give my application some resources. So let's give it 1 core and then maybe 2 MB of data for memory. And then port to expose. I know for my Docker file, I'm exposing port 5000. And then I'd like to add public internet access to my application as well. I already have DNS configured with my Kubernetes cluster. So all I'm going to do is say, we'll call this scissors, because I like picking scissors and rock, paper, scissors game, the MD Azure SBX, which is our domain, connected to azuredns.com. And we'll go ahead and click deploy. So we've gone ahead and Dockerized our rock, paper, scissors game. We pushed it up to Docker Hub, or at least we attempted to. I know I had it there before. We made a new application using the MassDriver CLI. We published that application to MassDriver, as we saw it pop up in the screen here. And then we configured it with the Docker Hub image that I'd like to deploy, and now we're running it. So this will take a few minutes to deploy. While we wait, I did want to mention that we do have more webinars coming up from members of our team at MassDriver. I have this webinars page here all ready to go. Next week, we'll be going over how to build a bundle in MassDriver. On the horizon for our webinars, we'll be going over how to upgrade Postgres, how to upgrade your Postgres version with no downtime, and how to run Azure OpenAI using MassDriver. We also have a community Slack that anyone can join. It's a great place to connect with our growing community of developers, engineers, and enthusiasts alike. So that's available at massdriver.cloud. Let's go ahead and check the progress of our application. Still running. While we have a little bit more time to kill, I did want to talk about the different runtimes that MassDriver supports for hosting your applications. Not only do we offer Kubernetes in each of the 3 major clouds, such as AKS, EKS, GKE, we also offer cloud-specific runtimes, such as Azure App Service, Azure Function App, AWS Lambda, GCP Cloud Run, just to name a few. All of our runtimes use Docker containers as their method for running applications, which means after this webinar, you should be able to Dockerize your application and get it up and running in MassDriver in no time. All right, let's check the progress. Okay, so it looks like it's finishing up here. Deployment is complete. Awesome. We'll go ahead and grab that URL that I set earlier, scissors, md-sbx.com. We'll paste this in my tab, and then there we go. I have my application up and running, so I want to pick scissors, and I won against, or I lost actually against the computer. I can play again, paper. You get the idea. So I have my rock, paper, scissors game up and running in Azure using Kubernetes and a Docker container. This concludes our webinar. Thank you so much for joining us today. I'll be sticking around to answer some questions. If you are interested in learning more about MassDriver, please check out massdriver.cloud. Thank you.